Hello and welcome to our live stream for this year's edition of Astropy, getting started with Mission Space Lab. My name is Fireball Fergus and I will be your host for the next hour. And I am delighted to be joined by some of the Astropy mission control team from the Raspberry Pi Foundation. Let's meet the team. Flying in from the outer space, we have Galactic G.
Hello.
Houston, we don't have a problem because Rocket Richard is here. Shimmering brightly, we have Halo Helen.
Hi.
And crushing it on the controls, we have Neutron Star Nick.
Hello.
And of course, we have you, our wonderful audience. Please let us know where you are joining from in the chat. It's brilliant to have you all here for today's live stream.
So what are we going to be covering today, Fergus?
Well, that's a very good question. Today, we are going to be telling you everything that you need to know about the European Astropy Challenge, an ESA education project run in collaboration with the Raspberry Pi Foundation. Today, we're focusing on Mission Space Lab, what your teams need to create for it, how to find all the information you need to get ready for the mission. And we have lots of materials to help you prepare, so we'll be getting you familiar with those. We will also be demonstrating how you can test your programs once teams have created them. This is really important because this will help your teams to achieve the goal of having their code run in space. There's plenty to get through today, but we'll try and make time for any questions at the end. So please post any questions you have in the chat as we go. So let's get started. It is my great pleasure to introduce Halo Helen, who's going to give us a quick introduction to Astropy.
Hi, everyone. It is a pleasure to be here. So what is Astropy? Well, let me tell you, Astropy offers young people the amazing opportunity to conduct scientific investigations in space by writing computer programs that run on Raspberry Pi computers aboard the International Space Station, or the ISS. The Astropy computers have some great names. They are called Nikola Tesla and Marie Curie, after the famous inventor and the influential physicist and chemist. Each computer is fixed with a sense hat and a camera that allows you to capture lots of different types of data. Long list for you. These sensors include, we have an 8x8 LED screen. We've got a gyroscope, an accelerometer, a magnetometer, temperature and barometric pressure sensors, a humidity sensor, and color and brightness sensors. Plus, there are two types of camera attached. One has a visible light camera, and the other one has near infrared. Astropy has two missions that young people aged between 6 and 19 can take part in, called Mission Zero and Mission Space Lab. For Mission Space Lab, teams of young people need to write a Python program that captures sensor or camera data and uses it to calculate the speed that the ISS is traveling in orbit as accurately as possible. Mission Space Lab is aimed at young people who are already familiar with Python or more complex coding concepts. Let's have a look at this short video from ESA astronaut Rosemary Coogan to tell us more about Mission Space Lab.
Hi Space Explorers, I'm ESA astronaut candidate Rosemary Coogan, and I'm thrilled to see your enthusiasm for the European Astropy Challenge, a project run by ESA in collaboration with the Raspberry Pi Foundation. As part of my training at the European Astronaut Centre in Cologne, I'm not only learning how to survive in space, but also delving into the fascinating scientific and technical details of the International Space Station, including its remarkable speed. So let's dive into the concept of speed on the ISS. Speed is a measure of how fast an object moves from one point to another. Up on the ISS, maintaining the right speed is essential to stay in orbit around our planet. Did you know that astronauts on the ISS travel around the globe much faster than any car or aeroplane that you've seen on Earth? But astronauts don't experience those high speeds like we do down here. That's because the ISS, including the astronauts inside, is in a continuous free fall around the Earth. We call this microgravity, and it gives astronauts the feeling of weightlessness whilst they're falling at an incredible speed. I'm very curious to experience this myself in the future when I finish training as an astronaut. But now the big question is, how fast is the ISS actually travelling? That's for you to figure out in this year's Mission Space Lab Challenge. By taking 2 photos of Earth with the Astropy camera on the ISS and comparing their location and time differences, you can use the magic of maths and coding to figure out exactly how fast the station is travelling around our planet. I wish you all the best of luck with the challenge, and we look forward to seeing your program run in space.
Fantastic. Thank you, Rosemary. So today's live stream is all about Mission Space Lab, and there are some really important dates for your diary to note down if you are considering participating. So grab a pen and paper or whatever you use to record dates on, and I'll give them all to you just now. So your first date is the 16th of January, 2025. We are going to be running another live stream for Mission Space Lab where we'll be taking lots of questions from the audience to help with any technical challenges you have while doing the mission. Your second date is the 24th of February, 2025. This is the deadline to submit your team's programs. Make sure you have registered before then, as you will need to record some team details before you can submit. Your next date is the 24th of April, 2025. This is the planned date that you will find out if your team will have their code sent up to the International Space Station. Though, depending on exactly what's happening on the ISS, it can change by a day or two. And then your final date is the 10th of June, 2025. This is the date that we plan to send out the certificates to all the teams and mentors who had their code run in space.
Fantastic. Thank you so much, Helen. That was an excellent introduction to Astropy and Mission Space Lab. So Mission Space Lab is a great way for young people to take part in some real space science. Like with real science research projects, Mission Space Lab has a particular problem that we are trying to solve. How fast is the ISS travelling in orbit? Rocket Richard is here to tell us more about this challenge.
Thanks, Fergus. Yeah, so as we've already heard, the goal of Mission Space Lab is to create a Python program that can run for 10 minutes on the ISS, and in that time, collect data from the Astropy computer sensors and camera and use that to calculate the velocity of the ISS. Now, once your team has written and tested their program, you can submit it for rigorous evaluation and testing by a panel of specialists from the Raspberry Pi Foundation and the European Space Agency. All programs that follow the Mission Space Lab rules will then be considered for flight status, which means they get to be run on the International Space Station for those precious 10 minutes. There's always lots happening on the ISS, which means the Astropis can only be used to deploy programs for Mission Space Lab for a limited time. But we always try to run as many programs as we can. So, what does your team's program need to output? Well, number one, your program needs to produce a numeric output of the average speed that the ISS is travelling. This is also known as the magnitude of velocity. Number two, the output that your program produces must be a text file, so a file with the .txt extension. Number three, the numeric output should use no more than 5 significant numbers. In other words, 5 digits in total, including decimal places. So, for example, 1.2345 kilometers per second. And that last bit's really important because number 4 is that the speed must be given in kilometers per second, no other units. And finally, your program should measure the average linear speed that the ISS is traveling around the Earth. As a mentor, there are a few steps that you need to be aware of to help teams take part. So firstly, you'll need to register as a mentor for Mission Space Lab at astropy.org/mission-spacelab. When you do this, you'll receive a confirmation email with links to register up to 10 teams. Then you'll need to register each team you're mentoring, and teams can have between 2 and 6 people in them. When you register each team, you'll receive an email with a unique link to submit their program. So after your teams have written and tested their program, it'll be time to submit their code. And you do that using the link you received. And you have to submit their code in a zip file. Remember, there's a different link for each team you register, so make sure you submit the correct code for each team.
Amazing. Thanks, Richard. So there's lots of information available on the Astropy, on astropy.org and on the Raspberry Pi Foundation project site. I'm going to spend a few minutes now to help you find your way around the materials. So on the website, you'll find information about the mission, the rules for taking part, and other eligibility criteria. Our project guides are what you will need to share with teams who are taking part. These are project guides, are what they will use when they are writing their programs. So let's have a look at what you can find where. So first up, you have the Mission Space Lab landing page on astropy.org. You've probably seen this page already, but this is where you need to go to navigate to other materials. On this page, you can find the video that we played earlier by Rosemary Coogan and general information about the mission, which can be really useful for getting young people interested to take part and form a team. From here, you can find 3 other useful resources. Number 1, the Mission Space Lab Rulebook. This page will give you the information about the requirements for your submissions and the rules for taking part. The ISS is an incredibly unique and secure environment to work in, so running computer programs up there means you have to meet strict security requirements as well as get your code to work. But do not fear, all of the information you need to meet the criteria can be found on this page. Next up, we have the eligibility criteria. Make sure you check this page because only teams from countries who are from European Space Agency members or associated states will have their code run on the International Space Station. You can find a full list of the countries and more details there. Then we have the Mission Space Lab Mentor Guide. The Mentor Guide walks mentors through each stage of the process to help your teams complete Mission Space Lab. Starting with registration, it then covers how to inspire and prepare teams. For running the mission, we have suggested trying out a design thinking process to help teams work through the challenge. Do check out this page because there are lots of useful tips and suggestions here to help facilitate the activity. For example, how to come up with ideas and prototype programs. There is also a great section about how to plan your program by looking at the different tasks it will need to perform and how it will flow. Finally, there is a section on submission where you'll find all of the information you need to make sure your team's code is formatted and submitted correctly. So that's our website. Next, we have our project guides. These are where you can find the instructions and example sections of code that your teams can use to create their programs. For Mission Space Lab, we have 2 main project guides. Firstly, there is the Mission Space Lab Creator Guide. The Creator Guide is the first place you should look for creating your program. In this guide, we introduce some code examples that you can use to develop a program that will run within the special environment of the Astropis on the ISS. We provide links to all of the Python libraries that you may choose to use in your program. You won't need to download all of them, but many will be useful for your program performing the task we have set. So do check out which ones you will need depending on how your team approaches the project. You might find that some of these libraries will not be the latest versions available. This is because the operating system on the Astropis, or Flight OS, has been checked and approved by ESA and NASA well in advance of your program running in spring 25. So some of the versions are the latest stable ones that were available in summer 2024. If you are already using Python on your computer, you may find that it isn't exactly the same version as being used by the FlightOS on the Astropis. The version that Astropis use is 3.11, Python 3.11. If you have the time and expertise, then you can try to make sure that your development environment exactly matches the Astropis. And this may be easier if you're using a Raspberry Pi, but it isn't a requirement, as we have produced a useful tool that will check your code is compatible. As long as you are not using a feature that was very recently introduced to a Python library, you should be fine. Your program will need to interface with the Astropy sensors, including the camera, and you can find details of how to do this and log the data in the creator guide. If you are using a Raspberry Pi, then you may have some of the hardware and can capture real data from your camera and SenseHat. Once you have created your program, you will need to test it with the Astropy replay tool. Even if you are using a Raspberry Pi, you should still use the testing tool to make sure everything will work on the Astropy computers and the flight operating system. We can't emphasize how important testing is. Finally, the last couple of steps of the creator guide show you how to format your finished program ready for submission. The second guide is an example approach for calculating the speed of the ISS using historical photos. This is a step-by-step guide that provides sections of code that build up to a final working solution for calculating the speed of the ISS using feature extraction from the images. This is more of a classic style Raspberry Pi project guide, so it does mean that if you follow this, you will have a working program at the end of the guide.
Thanks, Fergus. So, as we've just heard, there's two project guides that you can use, the ISS Speed Guide and the Creator Guide. Now, by combining these two guides together, you should have all the information you need to create your program. But it doesn't give you a complete working example. Your team will need to develop this themselves using their programming skills and make some design decisions about how their program will perform its tasks and give the outputs in the correct format. Here's a diagram showing one approach you could use. First of all, develop the algorithm that you will use to calculate the velocity. You could use historical data, for examples, the photos taken in previous missions, as described in the ISS Speed project. Remember, there's a working example of that in the guide already. The second step is to take that algorithm and wrap it up in such a way that it can be run for 10 minutes on the ISS. And that's where you'll need the creator guide. So if you were using the approach shown in the ISS Speed project, you'll need to modify your program so that it uses photos taken with the Astropy camera rather than the old image files. Don't forget that you have a 10-minute time limit for your program to run, so you might want to calculate the velocity multiple times and then take the mean value at the end. And, of course, don't forget to test your program. And speaking of testing, Galactic Geraint is here to tell us about how you can test your programs with the amazing Astropy replay tool.
Let's start by creating a little bit of example code to use to demonstrate how to test your submission or part of your submission as you go along. So I've just opened up Phony on my MacBook Pro and I'm going to start writing a small program. I have just imported the camera object and I'm going to import the SenseHat object. I'm going to instantiate the SenseHat object and instantiate the camera object. Then I'm going to take a photo called myphoto.jpg and I'm going to print sensehat.getTemperature. There we go, making sure to spell that word correctly. I've just saved this file and we'll use this file as an example to get started with. So when you've got some example code that you want to test or learn about, you might start by trying to run it into your editor. So I'm going to press the run button. However, if you find yourself without access to a Raspberry Pi camera or SenseApp like me, you will encounter this error, module not found error, no module named PyCam0, or perhaps you would see if the imports were in a different order, no module named SenseApp. Instinctively, if you've seen these errors before, you might think to try and install the packages. In Thonny, you can do this by going to Tools, Manage Packages, and I'm going to search for the PyCam0 library and try to install it. Unfortunately, these libraries are targeted at the Raspberry Pi OS only. So if you, like me, are running on a MacBook, Windows, or other Linux machine, you're not going to be able to successfully install these libraries. But even if you did manage to install them on Raspberry Pi OS, if you didn't have access to a real SenseApp or camera, you still wouldn't be able to run this program. So you would basically have very similar problems. What you need to do in this situation, what you need is some software that pretends that you have a Raspberry Pi camera and SenseApp connected to your machine so that you can use the PyCam0 and SenseApp libraries even though you don't have access to the real physical hardware. Enter the Astropy replay tool. This is a tool that we've developed that allows you to take pictures and readings from a pretend Raspberry Pi SenseApp and camera using the PyCam0 and SenseApp APIs. Instead of getting a module not found error, this program has just finished running and has been printed out some data to the command line. It's printed out real data readings and images captured from a previous mission, which I will just show you. Here is the image that I just took. The same code could be run exactly on a real Astropy or any other Raspberry Pi with SenseApp or camera with slightly different results. This Astropy replay tool run has just told me that it is 33 degrees Celsius, whereas if I connect to the Astropy on my desk and run a very similar program, I'm just going to import the SenseApp and I'm just going to instantiate it, and I will print the temperature as it reports it, and it says it's 23 degrees Celsius. So why the discrepancy? Well, the Astropy replay tool is replaying historic data from the ISS. So if I run the same code on the Astropy on the ISS, I will get the real temperature reading. If I run it using the Astropy replay tool on my MacBook, I get a reading from a long time ago, in this case from 2023. Similarly, if I try to take a photo on the Astropy on my desk right now, I will get a real photo of what my desk looks like. Quite messy, in fact, so I'd rather not do that. But if I try and take a photo using the Astropy replay tool, the Astropy replay tool replays a historic photo from a dataset back in 2023, and you just saw that image. So the same code can be run on a machine with or without an attached camera or SenseApp, the Astropy flight units and your own computer. So when you run code using the PyCam0 or SenseApp libraries on a machine with an attached camera and SenseApp, it will take a real picture or a real environmental reading from the SenseApp. But when you run it using the Astropy replay tool, the PyCam0 and SenseApp functions return data and photos from a historic dataset collected on the ISS back in 2023. If you repeatedly take a picture or repeatedly take SenseApp readings, why don't we do a SenseApp reading in a for loop, you will notice that the readings change over time. Let's just do 100 and print sense hat got get temperature. We'll do that 100 times. If you press the green button, you're still going to get the no module name sense hat, but if I run it through the Astropy replay tool, I'm going to get some data, which does change over time. It's not the most variable data point, but you can see that it does change over time. If I take, perhaps a better example is by taking photos. So if I create another camera object, and this time take 2 photos, I'm going to call it image1.jpg, and in the next line I'll copy and paste that, but just change it to image2. If I rerun this with the Astropy replay tool, I'm going to end up with 2 images which are not exactly the same. They will look similar. If I open image 1, you're seeing my photo rather than image 1. I'll just put that on this screen. Image 1 on the left and image 2 on the right. Although they look very similar, they are actually slightly translated, the viewpoint, and that's because the ISS has moved in the time it has taken between those 2 images. And that will form part of your solution for estimating the speed of the ISS. So, how to install the Astropy replay tool? If you are just getting started, we would strongly recommend that you use the online version of the tool, which you can access by going to missions.astropy.org/msl/replay tool. If you go to that page, you're going to arrive and see this interface, which allows you to submit a file, which should be called a main.py file. So let us use this same example. Why not? Maybe I'll change it just to vary it a little bit. I could, I don't know, set the brightness to 0.5 or something like that. I've just saved that file. Now I'm going to click and submit my main.py file. It says your submission is ready to run. Press the run button. So I will click the run button. And now the online replay tool is going to download the photos and data as well as the Python requirements before running the program. Depending on your internet connection, this could take quite a long time. In the meantime, I will show you how to install the offline version of the Astropy replay tool, which you've already seen me demonstrate. So we've created a Thonny plugin that integrates with the Astropy replay tool. If you want to install that, you need to go to the Tools, Manage Plugins dialog and type astro-pi-replay. Oh, I think I should have put Thonny in front of that actually. Thonny-astro-pi-replay and search. And the top result, Thonny-astro-pi-replay, you will install it on this screen here. I've already installed it, so I don't need to do that. Assuming you did just install it, the next stage to get things working is again going to the Tools menu, but this time to Manage Packages, and this time typing Astropy replay and searching, and then installing the latest version of Astropy replay. If you then restart Thonny, you will have this Astropy replay menu option here, which will run the code in your window using the Astropy replay tool, therefore circumventing the need for real hardware. Let's see if the replay tool has finished, the online version has finished now. So in my case, it's finished. It's reported that it finished after 2 seconds or so. The actual runtime obviously took a lot longer because I had to download those images, but the actual runtime was only 2 seconds. I can see those images that I took. It's saying that I didn't try to estimate the speed here, and I didn't create any other files or any other output. If I scroll down, I can download these outputs. I've just clicked the download button, and I'm going to open it up. And in Finder, I'm just going to hopefully open the images. It's image 1 there, and image 2 here. So it's just like before. There should be no difference or minimal differences between the two versions of the tool. The astute of you will recall that actually I had changed the brightness setting in my program that I submitted to the online version of the replay tool. And in fact, the images look incredibly similar to the ones that we took before using Thonny offline. And that's a very astute observation, because rather than being a full-blown hardware simulator, the Astropy replay tool is actually quite a simple data tool. It just finds the nearest data point or photo from a bank of data or photos collected from a previous mission and returns it. There is no simulation happening in software. So this leads to quite an important difference in behavior between code run on a machine with real hardware, a real attached camera or sense hat, and code running using the Astropy replay tool. So code running using the Astropy replay tool cannot modify future images or data. Although it ran correctly on the online version of the replay tool with this line, with no errors, it didn't have any effect. So more concretely, on a Raspberry Pi with an attached camera, it is possible to set the camera settings, image size, brightness, white balance, gain, etc., using the PiCam0 API. These settings will then go on to affect the look and feel of future images. On the Raspberry Pi replay tool, though, setting these camera properties, although it doesn't cause an error, it doesn't have the desired effect. It has no effect on future images. They are just being replayed from the historic dataset. So these images are in fact exactly the same as before when we ran it through Thonny without the brightness line. This is a limitation of using the replay tool compared with real hardware, but in practice, there's rarely a reason to use manual camera settings on the International Space Station because the lighting conditions will vary very significantly during the 10 minutes that you're given. It's much better to allow the camera to decide which settings to choose, and you will most likely get better results this way. So, using either the offline or online versions of the Astropy replay tool, you can start writing and testing your solution pretty much straight away without the need for real hardware. Why not get started now and test some of the code in the Creator Guide?
Fantastic. Thanks, Gawain. And such a great way to make testing your programs as easy as possible online or offline. So let's do a few shout outs and then we'll get into some questions as well. So if you have any thoughts or questions, please do put them in the chat now and we'll try to answer them as best we can. I know there's been a few in there already. But a few shout outs first, just to say thank you for joining and acknowledging the time you're putting into your preparation as a mentor for Mission Space Lab. So thanks for joining Mark in Canada. We have Majami, E2A and Maria in Finland, Krolik and Daria in Poland, Despina in Greece, Lisa in Denmark, Vivian in France, Chris in London, Gunther in Austria, Karel in the Czech Republic, and Liam in Ireland. Thank you all for joining, and everybody else that's here as well. if you have any questions, we've got a few to answer straight away, but please do add more into the chat as we go. So first question is that we've had, how can I see my teams and have I registered, that I have registered? So as a Mission Space Lab mentor, you register as a mentor and then you will receive an email confirmation. And on that confirmation email, there is a link to register each of your teams. So each team has a separate registration form. And you can, if you've registered one team, then you can just refresh the page and you can add a new team. And for each team that you register, you'll get a confirmation email for that team. And in that email, there is a link to submit the code for that team. And it's a unique link for each team. So make sure you put it somewhere safe in an email folder when you get them. So our next question, we had, could we use, can we use a Raspberry 5? Would anybody from my Astropy mission control team like to come in and answer that? Richard, Rocket Richard is here. Would you like to answer that question? Richard, very sorry, I think you're on mute.
Always one, always one. Yes, that's good, because what I was saying didn't make sense. I'll say it better this time. So yes, you can use a Raspberry Pi 5 computer, but you just need to remember that it's a more powerful, faster computer. So if you're using it in your program to do lots of intensive computation, it may run much faster on your Raspberry Pi 5 than it will do on the Astropis on the International Space Station, because those are using Raspberry Pi 4s.
Fantastic. Thank you, Richard. So there was a question as well, which we've kind of answered a bit in the chat, but I'm going to ask Galactic G to come back on to explain a little bit more. But the question was, how come the tool can be a bit slow running sometimes? So Gawain, would you mind?
Sure. Yeah. So, yeah, good question. The tool in the background is downloading a 10-minute sequence of high-resolution photos and the accompanying SenseHat data along with that. That bunch of files comes in at around 450 megabytes. So before your program is run in the background, even though you've pressed the run button, it will start downloading those files. Once it has downloaded those files, it will then move on to downloading the Python files that it needs to run and understand the program that you've submitted. So that's also quite a lot of files to download. So we're looking at around 500 megabytes of data being downloaded before your program is run. So depending on your internet connection, that can take a very long time. But if you do leave it in the background, it should eventually finish. Once it's done that, then the runtime clock will start. So when I showed you earlier, my program that I submitted took about 2 seconds, but the actual time from when I pressed the run button was a lot longer because it had to download those photos and data. So I hope that makes sense.
That's brilliant. Thank you very much, Gawain. And okay, so there's the next question we have is, how do I update my or my team's details? And this is a question we get quite a lot to our inbox, so we thought we'd answer it now. But basically, you can to update your details during the challenge, you can email us at contact@Astropy, which you should see on your screen rolling across the bottom now. So if anything changes during the challenge while you're participating, your details or your team, then you can just email us and we will update them. So that when it comes to the end of the program and your team gets a certificate, then all of the details are correct. So make sure you let us know if anything changes during the challenge. We have another question, which I think is probably for Galactic going again, which is how can we estimate the time it takes the program to run? So I think this is when we're testing the program rather than when it's running on the ISS itself. So Galactic going, are you still there?
I am still there, yes. So could you repeat the question for me?
So the question is, are we able to estimate how long it will take the Astropy replay tool to run a program?
In its online version, I think the question's referring to. So
yes,
as I said in my answer before, it's downloading about 500 megabytes worth of data. So if you know your internet download speed and you know roughly it's about half a gigabyte worth of data, you should be able to do a calculation, quite a simple one, to work out how much time it will take before your program starts running. So the total time you're going to have to wait until you reach the final screen is going to be the time that it takes for you to download the photos, and plus the runtime of your program. Depending on what you do with your computer whilst you're waiting, the runtime of your program may change. So I would advise that you run your program and leave the computer as is, because if you start watching a YouTube stream such as this one, your CPU might end up being overloaded, and consequently the Python runtime will take a little bit longer than you might expect. This is a problem that you might encounter on the ISS too if we happened to be running something in the background of the Astropys. One Python code line might take longer each time we run it. And that's just something that we have to live with when we run programs on the operating system. But if you do try and control your environment that you run in, so if you run on the Astropy replay tool and leave your browser window just in the background and just leave your computer alone, you should get fairly consistent results, assuming that you have a reliable internet connection. So I hope that answers your question. Good question.
Brilliant. Thank you, Gawain. Our next question is, will the code definitely run during the day so that photos are possible? So this is when the programs are running on the International Space Station, and Rocket Richard is back to answer that one.
Thanks, Fergus. Yeah, that's another really good question. Let me tell you a bit about how we actually run your programs on the ISS. Obviously, or unfortunately, we don't get to go up there and press buttons, so everything is run automatically. And what we do is we upload a whole batch of programs, and we have some software we've written that runs on the flight unit, and it automatically runs them one after another. But we've added in some clever intelligence to that software so that it knows whereabouts in its orbit the International Space Station is, and if it's in darkness, it doesn't run any programs. It will always wait until the Earth below the ISS is in daylight, which is a long way of answering your question by saying yes, it will always run during the daytime.
Brilliant. Thank you, Richard. So we've got a question in the chat from Chris, I think, which is about registration. So are you able to kind of manage your teams, or does Mission Zero have the same registration process as Mission Space Lab? And the answer to this is no, it has a slightly different registration process. So if you're familiar with Raspberry Pi, Mission Zero has something called the Mission Hub, which is linked to the Raspberry Pi accounts. So it's kind of part of that ecosystem. And Mission Space Lab follows a slightly different process. So when you go to register for Mission Space Lab, you receive an email confirmation as a mentor, and then you need to register teams, and you'll have links in your registration email when you register as a mentor. And then when you register a team, you get another confirmation email for that team specifically. and in there is a link to the code to a link where they can submit their code as a zip file. So a slightly different process. I have another question, which I think is for me, which is how can someone who is not from or not based in a ESA state participate? So unfortunately, there are some limitations here because this is a European Space Agency program. It means that all of the European Space Agency members fund and help support the European Space Agency. So it does have some limitations on who can take part, being only the countries who are part of the agency or associated with it. But it doesn't stop you from doing the activity, and we would really encourage you to still do the activity and make use of the testing tool, the Astropy replay tool, for example, because that is really quite unique data that we captured from the Astropys on the International Space Station earlier this year. And so I think there's still a great deal of value in terms of the learning outcomes for teams, even if they're not, unfortunately, able to have their code eligible to run on the space station. Next question then, we have, what is the main goal of Astropy Mission 0? And I'm going to hand back to Rocket Richard, who's going to tell us more about that.
Thanks, Fergus. Mission 0 is a super cool program. It's designed for beginner and intermediate learners of Python. And the goal is pretty simple. You'll get to write a program that in 30 seconds or less will display a beautiful picture on the LED matrix of one of the Astropys. And if you've been looking at the Astropy I've got in my room at the moment, it's currently showing some beautiful entries from last year's Mission 0 competition. So the idea is you create a lovely piece of pixel art, and then you use the color sensor, which is just behind here on the Astropy, to measure the lighting conditions on board the ISS, and then adjust your picture to take account from those. So for example, you could make the background of your picture match the ambient lighting in the ISS. That's it. That's all you have to do. The great thing about Mission 0 as well is you can enter it all online using your web browser. And normally that activity takes about an hour and an hour and a half to run. We know that the astronauts love seeing those pictures on the flight units. It really brightens up their day. And we have a nature theme. So the idea is you send them a picture that reminds them of life on Earth.
Awesome. Thank you, Richard. I think we have time for just a couple more before we wrap up. So, excuse me. First question is, can we use the Google Coral Machine Learning Accelerator that is on board the ISS that some of you may be familiar with? And I'm going to ask, actually, who from the team would like to drop in here? I guess Richard or Geraint are probably best placed. Geraint, would you like to come in for this one? Or Richard? There we go.
Accelerators are still available on there. At the moment, we're in the process of updating the operating system on the flight units on board the Astropy. We talked about it earlier, the Flight OS. And so it's not 100% certain that the Coral dongle accelerators will be working this year. So if you do have plans to use the Coral dongles, please get in touch with us at the email address that you'll see at the end of it, and we can discuss with you the best way of writing your program. There we go, contact.astropy.org down the bottom.
Fantastic. Thank you, Richard. And then we've just got one more question, and that's, will this recording of the live stream be available to watch back? Yes, it will. It will be available on YouTube, and it will be staying there for as long as possible. So if there was anything that was unclear, do watch it again. If there's anybody that you know who might be interested in being a mentor, or taking part in Astropy Mission Space Lab, then do share it with them. And hopefully we've managed to answer most of your questions and meet some of the aims of this live stream in familiarizing you with the different resources, the challenge itself, and how to test your programs wherever you are. So great questions, everyone. Thank you very much. I'd like to invite all of the team back just for a moment, if that's okay. I'm afraid that's all we have time for today, but don't worry, we have another live stream happening on the 16th of January at 5:30 Central European time. And at that live stream, we will take lots of questions from the audience to help you troubleshoot any issues you have with your programs. We'll be sending out a newsletter with a form to submit your questions for that. So make sure you visit astropy.org, address on the screen in a moment, and subscribe to our newsletter to get the details. In the meantime, you can get in touch with us at Astropy Mission Control by emailing at the address on your screen. If you have any questions, please don't hesitate to get in touch. So thank you everyone for joining our live stream today. We look forward to hearing from you and seeing you at the next one in January. Until then, it's goodbye from everyone here at Astropy Mission Control.
Bye.
Bye.